Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Going to continue, and our next speaker is Ravishankar Krishnaswamy from MSR India, and he'll tell us about online buy-at-bulk network design.
Thanks, you all, and it's a pleasure to be here. So I'll be talking about a network design problem called buy-at-bulk network design, and hopefully by the end of this talk you would have understood the model and the sort of results that we can get in this model, and some flavor of the techniques that we have. So none of the proofs, I won't go over any of the proofs, it will just be a very high-level overview of the work. So it's joint work with Deeparnab, also at MSR India, Alina, who's at Awerbuch, and Debmalya, who was a postdoc here and currently is faculty at Duke. Okay, so let me start off by talking about multi-commodity flows in general. So it's a very classical problem in optimization. So you're given a graph, undirected graph, let's say. Edges have capacities, and you're also given a collection of demands, sources and sinks. For simplicity for this slide, let's assume all demands are 1. And so the question that we ask is, does this graph admit a unit flow that you can simultaneously route from each source to the corresponding sink? And in general, so this is a toy example here. So you have this graph, let's assume all capacities are also 1, and there are these source sink pairs. So the red vertices form a pair, green vertices blue, and you ask, is there a routing of 1 unit of flow from all the sources to the sinks concurrently? And in this example, the answer turns out to be yes, and you can find a routing and so on. And so it's a very fundamental problem in optimization. So it comes up in a variety of places, and people have designed a lot of algorithms for this problem, like near linear time. So we've optimized runtime, we've optimized like various conditions under which you can find integral routings and so on and so forth. So it's been studied very extensively. Okay, so what we are focused on, what this line of buy-at-bulk network design, what network design in general focuses on, is how do you design the network which routes this flow. So given a network, finding a flow is the flow problem. We're looking at one level above this optimization. So we're trying to design networks which can support good flows. Okay? So this is sort of the problem that, say, AT&T would be interested in. So when it's building the infrastructure for USA's internet network, so it would be interested in such a problem. So it knows sort of how much demand is there which wants to send packets of data, and it has to try to build the cheapest network which can route this flow. So that is what is called the buy-at-bulk problem. So it's been studied since the 90s. So let me just describe the problem. So here you are given again a graph G and the collection of demand pairs. So let's say AT&T has somehow managed to estimate the total demand that wants to go from various cities, various sources to various sinks. And each SI-TI pair also has a number Di, which is the bandwidth that SI wants to send to Ti. And so you could think of like our house as being SI and the Netflix server as being Ti, and this 10 Mbps I want dedicated pipe of 10 Mbps while I watch the movie or something like that. And additionally, AT&T is faced with cable types. So for every edge in the graph, there is a collection of possible cable types, so fiber or optical network or copper wire or so on. And each of them can provide a certain capacity and they come at certain price. So this is the optimization AT&T wants to do. So what it has to do is it has to buy cable types so that you can actually provision bandwidth to support concurrently all the flow that's possible. So we have to buy as few a cheap collection of cables so that you can route all the flow that's possible. Okay. So, and what's the objective function? We want to just minimize the cost of all the cables that we have bought. So here is a very simple toy example. So let's say there is one source, one sink, and there are 2 edges in this graph. You could directly take an orange cable, which is a very high bandwidth. So it's 1000 bandwidth and cost is 300. Or you can take 2 hops using a blue cable, and each of them is 50 units cost, but they give me 100 bandwidth. And let's say the total demand is 2250. In this case, you could just buy 2 cables of the first type and 3 cables of the parallel bottom path, and you can find that there's a cost of 900. If the demand slightly exceeds, then you might shift the better solution might be to just buy 3 cables of the top portion. Already buying 3 cables of the orange kind has the same cost and it can give me bandwidth of 3000. So it's, as you see, if the bandwidth requirement increases over time, you should just not use the blue cable, and you should start using the orange cables. So the overall problem is you have a graph, and on each edge you have these cable types. They all have different costs, economies of scale, and you have to figure out how to buy which cable type so that you can route a given flow. So at an informal level, you can think of this as jointly optimizing a collection of knapsack problems. So every edge there is some little knapsack instance sitting there, and we want to figure out how much bandwidth to allocate on that edge and what cable types to buy on that edge so that the multi-commodity flow is feasible. Any questions about the problem?
Can you be more explicit about the link between your toy example and the knapsack problem?
So in particular, if there's only one edge and there are many cable types, so there's one edge S to T and there's a bandwidth of say 100, and I have multiple cable types, like each of them has a cost and a certain capacity. I need to figure out what is the cheapest subset of these cable types to buy so that can provide me the certain capacity.
Oh, it's like a covering knapsack.
It's a covering knapsack problem. And overall I have a graph, and now I want like these many covering knapsacks that I want to jointly optimize in some sense. Exactly. Okay. So as an example, this was I think in early 2000s, this was actually AT&T's physical net infrastructure. So they were using 4 types of cables, and each of them, depending on how long the cable type is used, there would be a different cost, and this probably is to satisfy the demand then that AT&T had. From, you can see a lot of demand in the northeast and this various parts. Okay. So the question that we are sort of interested in is how did AT&T optimize and build such a network, and more generally what are the types of problems that we can model using this framework. Okay. So this is a very general model, and it can capture a lot of different types of cost functions. So for instance, if the cost was equal to the bandwidth, then it would be like a linear cost function, and there's not really any economies of scale. You can just independently buy shortest paths and then find a routing and so on. Or you could have the other extreme, which is infinite economies of scale. So there's an initial startup cost, and after that you get infinite bandwidth. This is sort of like a very classical problem called the Steiner tree problem, where you just want to find the minimum cost tree that just connects up all the sources to the sinks. Again, a very fundamental, well-studied problem. In general, you could have an arbitrary concave function, which is also characterized by these cable types. So you can model a variety of problems using this in this framework, and that's what we are going to be looking at. In fact, we are going to be looking at an online version of this problem. So what is online? So everything is as stated. The only thing is that these demands arrive one at a time. So they arrive incrementally, and so this sort of captures, I guess, the fact that AT&T does not know ahead of time all the demand that it's ever going to provision for. So there is uncertainty in provisioning, and this is one way in which we have modeled uncertainty in certain problems. And so this is the model that we are going to be looking at. So you could think of emerging markets. So a new service could set up a data center, and a lot of demand could be going towards that. Or you could have a new city that just emerges, and then a lot of demand originating at that city, or various things. Okay. In fact, there is a new city that's being built in India as we speak. So that's one of the. Yeah. Okay. So, and what is the constraint that the online algorithm has? It cannot unbuy edges that it has bought in the past. So if it has already paid money and bought a certain link, it spent the money. So money spent is money used up. So it cannot unbuy and reclaim credit for that. So the standard notion, so this is an online algorithm, this is what we expect an algorithm to do, and how do we measure the performance of an algorithm? So the way we measure for online problems is this notion of competitive ratio. Okay, so what we want is the total money that the algorithm has spent over time until satisfying a certain demand. We want it to be comparable with the total cost that the optimal solution would have spent if it knew that this was the demand that it had to solve. So the denominator is just the optimal offline solution for the current input, and the numerator is the total money that the online algorithm has spent, and we want this ratio to be as small as possible. So that is the model this is the most commonly used model for online measuring the performance of online algorithms, and this is called comparative ratio. Okay. So this problem has been studied extensively since the 90s. So in fact, one of the earliest papers that introduced this problem also motivated the online problems. They said that the online problem, they motivated the problem in an online framework, but most of the results that we knew until now were, I mean, the offline problem is very well understood and the online problem was not as well understood. And the focus of this talk is going to be on the online multi-commodity problem. So demands arrive over time and we have to buy these links over time as well and be competitive with the offline optimal solution. So one work that's particularly relevant for us is that the online algorithm, for a very special case, when all the sources, all the demands have a common sink, think of all of us wanting to just use Netflix, in that case, then online algorithms were known for this problem. So in the general model, we did know online algorithms for this, but the general multi-commodity version we didn't know online algorithms, the general problem. Okay. And like I already explained, this framework captures a lot of other network design problems as well, like the Steiner tree and various group Steiner tree and so on. And a common theme across all of these problems is that, which is also true for our problem, is that the single commodity, non-trivial single commodity algorithms were designed before non-trivial multi-commodity algorithms. So we always understood the single commodity before we understood the multi-commodity, and similarly for online algorithms as well. So online Steiner tree was understood before online Steiner forest, online group Steiner tree before online group Steiner forest. The same for our problem, online multi-commodity single commodity byte bulk before online multi-commodity byte bulk. So is there a theme that's going on here is one of the questions. So what we show is we give a generic reduction for online problems from the multi-commodity version to the single commodity version. Okay. So we show that if you can solve the single commodity version, then you can use our reduction sort of for free and then solve the multi-commodity version also. For free in the sense that we lose polylogarithmic factors in the approximation ratio, but that's about as much as we lose. Okay, so as a byproduct, we get the first online multi-commodity byte bulk algorithm. And so a very important previous work for us, which we extensively build on, is a work that was a very nice algorithm by Chekuri et al., which gives a similar reduction for the offline problems. So it says that for offline problems, multi-commodity problems are almost as easy as single commodity problems. And you can think of our work as an online analog of that result. Okay, so that's basically pretty much the takeaway from our
Am I correct in remembering that the online single commodity problems, the competitive ratios are usually at least logarithmic to begin with? So in that sense, the fact that your reduction incurs polylog overhead, you're starting from an algorithm that's already polylog competitive.
True.
Yeah.
True. But yeah, so it's about, it's like comparing log squared versus log to the 7th or something like that. So if they're all polylog, then it's fine. But if you care about constants, then we do lose constants. Yeah, that's right. Okay, so any other questions? Okay. So essentially, our algorithm is sort of an online analog of this reduction theorem. So in an online manner, we reduce a multi-commodity problem to single commodity instances. So let me, since our work extensively builds on their work, let me go over the high level approach that they follow. So what they show is a very nice decomposition that says that I can decompose a multi-commodity instance into a collection of single commodity instances such that two properties are true. Firstly, in this decomposition, every source and sink are connected to the same in the single commodity instance. So they basically find many hub instances, single commodity instances, such that for every pair SI/TI, both SI and TI connect to the same hub. And
You mean their neighbors in the graph?
oh, not neighbors. You can think of, let's say I want connectivity to Netflix, then they find a certain hub, let's say Chicago, where both I connect to Chicago in a path and Netflix also connects to Chicago using a path. So the next slide should make it clear. Okay. And furthermore, they show that if you independently solve these single commodity instances and add up the cost, overall it's small. It's logarithmically factor worse than the actual optimal solution. Okay. So to illustrate, you can, let's say the original optimal solution is something like this. So the blue pair is connected using some path, the green pair is connected using some path, and so on. it's not necessarily very structured and you don't know this. What they show is that I can decompose this instance into a collection of these hub based instances where you can see both S1 and T1 connect to this hub, the orange pairs connect to this hub, the pink pairs connect to this hub and so on. So they not only show the existence of a decomposition, they also partition the sources and sinks into the correct buckets. So they
when you say connect to a hub, you mean that their only connection is going via this hub?
Yes. So once you know this, you can, and you know the partition, you can solve the single commodity problem for each of these separately. Does
it kind of follow from tree embeddings?
Almost, because it's there are two, the cost and capacity, right? So it's not quite a tree embedding result, but it's almost, you're right. Yeah. So what they show is that you can always decompose an optimal solution into this sort of a partition, such that if you add up these costs separately, it's at most, it's not too much worse than the original cost. Okay. So given this existence, how do they find the partitioning? So they actually use a very greedy like algorithm to find the partitioning. So they iteratively find the best hub and the best set of sources and sinks that each connect to this hub, peel out that subset of demands, then find the next best hub and so on. So they, in a greedy fashion, like set cover, akin to set cover. So you can think of each tree as a set and you want to cover all the terminals using these trees, so they can find a greedy like algorithm to solve this problem. Okay. So it's very nice analysis, but it's also inherently offline because you need to know all the sources and the sinks to run a greedy algorithm. So you find the best subset, remove it, find the next best subset, remove it and so on. Okay, so to motivate our algorithm, let's look at a modular view of this Chekuri et al.'s algorithm. So what they show is they can partition the demands into these common hubs. So they can assign each demand pair into a certain hub such that if I solve these single commodity instance independently, if I find the best cables for just connecting these, find the best cables for this and this, put them all together, that's not a bad idea. So that's what they show. What we are going to show is, what we are going to do is just make both of these steps online. So we make our assignment algorithm online and so in some sense when a terminal pair comes, we decide which hub should they both connect to. So if I want connectivity to Netflix, then our algorithm will say, okay, let me connect to Chicago, Netflix also connect to Chicago, and then the choice of Chicago is what our algorithm makes. And so for each terminal, once it arrives, it immediately says go to this hub. And so this we do online. And if our partitioning is good, then we can like follow from previous work. So then all we need to do is just run online algorithms for each of these common hubs and put them all together for our solution. And what our main result is that this assignment can be done online in a reasonably good way. Okay? So there is an online assignment scheme where the cost of these independent solutions, if you add them up, it's not too much worse, and there's only a polylog factor that you lose. So after this, it's a corollary to say that the multi-commodity algorithm works. So how do we solve the online problem? So essentially we use linear programming. So we first try to find an assignment which is fractional, and then later we round this to make it an integral assignment. So to better understand the next slide, let ZIR denote a fractional variable. It captures the extent to which this SITI pair is sent to this hub R. So we have, for every possible hub, we will have a variable which says how much of this SI and TI both want to connect to this hub. So that is the variable, the main variable in our LP. So what's the LP? So firstly, we want every SI-TI pair to be connected to some hub. So summation ZIR over all possible hubs is at least 1. And then we have several single commodity LPs inside this overall outer LP. So each LP sub R tries to satisfy SI and TI. So all the terminals that are assigned to it, this LP tries to satisfy them to the extent that the LP decides. So it's to the extent of ZIR. So this is what I call the outer LP, and then there are several inner LPs for each hub solution. And the objective is just to minimize the sum of all these hub-like solutions. So firstly, from the offline decomposition result, we know that this LP admits a good solution. So there is a good solution which is at most log n times worse than opt for this composite LP. So already I have split up the overall multi-commodity into a collection of single commodity instances. And there exists a good solution, it's whether we can find it online, that's the main question. So two questions. So firstly, can we solve this problem online well? Can we solve the fractional version online? Secondly, can we round it? So these are the main questions that always come up with online LP based approaches. So for the first question, you will have to take my word for this, but I won't go over the details, but you can solve this LP online fractionally. Okay? The rough idea is to, it's an algorithm inspired by the online set cover algorithm, which is sort of like the basic algorithm that many online algorithms use. So we roughly increase our assignment at a rate inversely proportional to the cost increase to a hub. So SI and TI are assigned to a hub R at an inverse rate to the increase in cost if I assign it to a hub R. So if I assign both SI and TI to Chicago and the cost increases a lot, then that assignment is not favored over some other assignment where the cost increases less. So it's, notice that this is not a static variable, it's how much the LP dynamically increases. So this is slightly messy, but this is at a fundamental level it's pretty simple. Okay. So it's not also what I say will not be very illuminating. So just take my word that such LPs can be solved online fractionally. Okay, so in fact for a large class of these LPs you can actually find fractional solutions pretty well using a multiplicative weight style of an algorithm. Okay, so therefore we can actually find a fractional solution to this LP online, which is only a polylog competitive compared to the optimal solution. So this can be done. So the question now is, the second question that remains, second and only question that remains is how do we round this LP? But here there is a problem. It won't really be a problem, but so there, at this moment there's going to be a problem that we don't necessarily know how to round these LPs online. So online rounding is a very difficult game in general. So and this LP furthermore is very complex. It's not even online set cover. Online set cover has a nice rounding, but many online problems we don't know how to round things well. So what do we do with just having a fractional solution? So our idea is that we don't necessarily need to round the LP, we just round the assignment, the outer variables. We can leave the inner variables completely fractional and we'll argue that that's still okay. The only thing to do is rounding the outer variables. Okay? And that rounding is very simple. So what's the rounding? Every hub chooses a uniformly random number between say 0 and 1 and scales its LP solution by that number theta. Okay? So essentially each of the inner LPs are randomly scaled by some quantity, random variable. And how does the SITI get assigned to a hub? So we just do the simple thresholding. If ZIR is at least this random number theta, then assign SI and TI both to this hub of R. Okay, so this simple calculation will say that every SITI is assigned to a hub with constant probability because summation ZIR was at least 1. Furthermore, each scaled LP can fractionally route the assignment. So we have scaled by this theta R and ZIR was at least theta R. So fractionally the inner LPs can satisfy the assigned terminals. Finally, the expected cost of every scaled LP is small because it's simple scaling by 1 by x and x is randomly between 1 and 1 over n. So the expected value of this is just log n. So what we have done is found a fractional solution to this with the restriction that the ZIRs are integral. Everything else can be fractional. Cables are still bought fractionally by this, but the ZIRs alone are integral. And the overall cost is pretty competitive with respect to opt. Okay. So after this we are sort of almost done. So why? The reason is, even though we don't know how to round the inner LPs, we know that the inner LPs are good. So the integrality gap of each inner LP is small. Okay, so what do I mean? So after the previous slide, we have shown that the sum of the fractional costs of these inner LPs is at most polylog times opt. And the integrality gap of each inner LP is small, which means that is because we know offline rounding algorithms for the inner LPs. Therefore, the sum of the optimal solutions of each inner LP is also small. So our assignment, so this gives us a certificate that our assignment did not screw up, and that is all that we care about. Okay? So our online assignment scheme is good. It is pretty much all that I wanted to show outline. Okay? And if we know that our online assignment is good, we can just run the existing online algorithms and we can put the two together and complete it. Okay, so what is the overall summary? So we had a multi-commodity instance, and what we used an existence of this decomposition result to formulate a composite LP and then solve it online. And we only partially rounded the outer variables and then use the existence of small integrality gap of the inner LPs so that to get confidence that our assignment was okay. After that, we can just feed it to the appropriate online single commodity instance. So each hub will be running a single commodity algorithm. So you just feed it to appropriate hub and then put all the solutions together and recover our solution. Okay, and to conclude, so we studied this online buy at bulk problem and two open questions. So one is a very broad loose open question, one is a very concrete open question. So the loose open question is, where else can we use such a partial rounding approach, where I only partially round certain variables, keep certain other variables not rounded, and then do something with it. The concrete open question is, here I could allow buying multiple cables, so I could buy the same cable many times. So there are certain applications where I cannot buy the same cable many times, so each cable can be bought only once. And that even offline, one source, one sink, that problem is wide open. So we don't know how to approximate the following network design problem, where I have a graph and I have certain cables. I can buy each cable at most once, and there is a single source and a single sink wanting to send a certain flow, and I want the cheapest network which can support that flow. And that's we don't know how to solve that problem.
You mean, what is the approximation mentioned there?
There's no non-trivial. I think, yeah, very bad approximation. Maybe like n or something. I don't know. Yeah, so that's pretty much it. Thanks.
Thank you.
Any questions?
Opening half, you were talking about this tantalizing question whether multi-commodity was inherently harder than single commodity online buy at bulk. You showed it's at most polylogarithmically harder. Is there any super constant separation known between the competitors?
I would think so, but I won't bet any money on it.
Later now you have it's the basic multi-commodity
That's
flow.
for offline.
Yes.
That's for offline.
I'm not sure. Anything else? Okay. So now we have a longer break. Let's thank Ravishankar.